Here we're going to look at question 74 from the IMAT 2011 paper. So in this question, we're given two different scenarios. We have a 50-gram ball in one fluid, which has a density of 2.5 grams per millilitres, and we're told that in this fluid, our 50-gram ball just floats. So if we were to put it in the liquid submerged, it would just stay at a stationary height. Then we're told we take this ball out and we put it into a second fluid, which has a lower density of 2 grams per millilitre, and here it sinks. So the ball is going to sink through the fluid until it lands against the bottom of the beaker, at which point it's going to have some force from the beaker pushing back up on it, and some buoyant force due to the liquid. So what the question asks us is, what is the force for object on the container in our second scenario here? So if you'd like to have a go at doing this question yourself, then please pause the video now. Otherwise, let's have a go at doing it together. So to answer this question, we might think about some of the principles and rules which we can use to help us answer it. And I've already given a bit of a hint by talking about the buoyant force acting on our 50-gram ball in this second case. And there is actually a buoyant force on the ball in both cases. That's how it's floating in the first one. And buoyant forces are generally governed, at least at this level, by Archimedes' principle. And Archimedes' principle basically states that the upward buoyant force due to a liquid is equal to the weight of liquid displaced by an object. So, what that means basically in this case is that, say we look at one, we have this ball here, there is an upward buoyant force which is keeping the ball level, so this force is equal to the weight of the ball. But we know that this buoyant force is also equal to the weight of the liquid displaced. So, we can use this rule to say that the weight of the ball is going to be equal to the weight of the liquid displaced in this first scenario. So, if you like, you can sort of think of this as the ball not really having any physical properties different from the liquid. And of course it does, because it's chemically going to be different. But to the liquid, it just has the same density. It just sits there and floats as though it was some more liquid. So having the same weight means that the density of the ball is going to be the same as the density of the liquid. It's going to be 2.5 grams per milliliter, or D1 as we've called it. Then, with this density of the ball, we can go ahead and just figure out the volume of the ball, which is going to be its mass divided by its density, which we can of course substitute in to get a volume of 20 millilitres. Okay, so you might at this point be wondering why this volume of the ball is actually going to be useful, 20 millilitres. Well, we spoke about in this second scenario, we have our ball and it's against the bottom of our container, and it has some buoyant force due to the liquid, and it has this reaction force due to the container acting on it, to counteract the weight of the ball. So, to find the force of our object on the container, the reaction force, we need to find the buoyant force to take that away from the weight. So let's go ahead and try and find our buoyant force in this second scenario. Now I know the volume of the ball is 20 millilitres, so it means that 20 millilitres of liquid is displaced. So we need to try and find the buoyant force by using Archimedes' principle. And we need to find the weight of the liquid displaced. So to do that, we can find the mass displaced, which of course is just going to be the volume of 20 millilitres multiplied by the density, which is 2 grams per milliliter in this case. So we know that we have 40 grams of liquid displaced. This 40 grams is going to have a total weight of mg, the mass, multiplied by the acceleration due to gravity, or the gravitational field strength, which we just take to be 10, giving us a weight displaced of 0.4 newtons. And therefore the upward buoyant force is also going to be 0.4 newtons. Then, just before we try and find the reaction force due to the container, we can just find the weight of the ball at this point rather than doing it in a second, and we find that the weight of the ball is going to be 0.5 newtons as well. So we can move on and think about the forces actually acting on our ball in this second case, with the weight acting downwards, this force, the reaction force F, acting at the point of contact, and of course we're going to have this buoyant force of 0.4 newtons as well. So to find the reaction force F, we just have to go ahead and take the buoyant force away from the total weight of 0.5 newtons to get a reaction force of 0.1 newtons. So this is going to be our final answer, and it's going to correspond to answer A that we're given in the question.